Today I have selected two different topics for my talk that allow me to illustrate you the powerful of large-scale facility, and by large-scale facility I mean neutron and synchrotron radiation sources. I think it is important that we start to use and to exploit as much as possible this kind of sources because they are available, and we can have access to these sources if we make good proposals. So I think we must to have good scientific topics to submit to the committees at the synchrotron and the neutron sources in order to have access to this important possibility to improve the level of science that we can do. Of course, I mean, this does not mean that we have to stop our laboratory works. Our laboratory works is fundamental. Without laboratory works, we cannot go to the large-scale facility. We can go to large-scale facility only if our sample have been very well characterized in our laboratories. Okay, so basically two materials are completely different, but there is a binding connection, and this means that both of them are of potential interest in solid oxide fuel cells, because the first example deals with material that can provide oxygen, because they are oxygen conductors, and the second one will deal with materials that can store and release hydrogen. So which are the two necessary elements to make a solid cell fuel cell working. So the first one is a mixed oxide, is strontium cobalt oxide, and its particularity is that it is able to change the stoichiometry from oxygen 2.5 up to oxygen 3. Which is a huge amount of possibility of oxygen intercalation. And even more interesting is the fact that this material, but also the homologue with iron, so if we put iron instead of cobalt, it will work in the same way, and it is able to do this job at room temperature 100 electrochemical condition. This is very important because you have to imagine that oxygen 2- is a very big sphere. It has 2.3 angstrom in radius, 1.3 angstrom in radius, 2.6 in diameter. So it is very difficult for oxygen to migrate inside a solid. Normally, oxygen conducting materials works at very high temperature. And so it is quite impressive that there are some materials that are able to do this job at room temperature, and we are willing to understand why. So these materials in the oxygen 2.5 state have a bromine-millerite structure. This means that in a simple way, the system is much more complex, but we can imagine that we have an alternation of blue and red layers. The blue layers are octahedral sites for cobalt or for iron, and the red one are tetrahedral, okay? And when we are adding oxygen, we change the stoichiometry, and at the end we have a cubic perovskite, which are much simpler structures. Now, of course, we want to investigate how it is possible to move from oxygen 2.5 to oxygen 3. As we are dealing with crystalline material, we will run diffraction, but we will not run X-ray diffraction, but neutron diffraction, because the element we are interested to is oxygen. And oxygen has a very low X-ray scattering power with respect of the heavy cobalt and even heavier strontium. So the same experiment done with X-ray would lead to a much less contrast in what we are looking for. So the technique of choice in this case is neutron diffraction, neutron powder diffraction, because we are dealing with powdered materials. So this has been done in situ at the neutron source at DLL, D20 diffractometer. This is a 2-day experiment, and we have imagined that we have an electrolytical cell, and we run in situ the diffraction. You can see clearly that the peaks of the bromelain fight progressively goes down, while the peaks of the cubic phase start up. In a given region, we see some superstructure peaks as well that somehow we have to understand. So this is the evolution of the potential during the experiment, and we see that basically we have three regions. The first region up to a charge transfer of 0.5 electrons. This means that we reach the intermediate stoichiometry for oxygen 2.75, which is exactly in the middle in this transition. We have in first approximation no change of potential. This means that we are dealing with a biphasic system, and we have always the same phases. This means that immediately the first oxygen that goes there forms immediately a small fraction of the strontium cobalt oxygen 2.75, and we have the remaining part that still has the bromine layered phase. Of course, the fraction of these two phases changes in time till we reach the complete strontium cobalt oxygen 2.75, which is a deficient cubic perovskite. And we will see this better from the Ritzel refinement in the next picture. Then the potential changes importantly here, and here we reach this means that in this case we have only one phase, and this phase is changing. This means that moving from strontium cobalt oxygen 2.75 to oxygen cobalt 3.0, we have the same phase in the whole solid that progressively changes. So this is better seen maybe in the result of the Ritzel refinement. So we have a biphasic refinement with two phases. So the starting bromine phases goes down, and the deficient cubic perovskite goes up. And here are the refinement, very important. This is also testified by the fact that the cell parameters are not changing, because we have always the same two phases. Simply, we are changing the relative ratio of the two phases. But when we reach this point, something happens. So we stop having two phases, we have just one phase. And in this case, by adding oxygen, we see a change in the lattice parameter. These are the intensity of selected peaks that are the more intense of the different phases. This is the superstructure peaks that appears in this region, and this is the refinement of the oxygen fraction in the last part of the diffractogram. So oxygen 2- is entering the system. How is the charge balanced? Because we must have a neutral solid at each steps. Of course, the trick is that the transition metal, cobalt in this case, but iron will do the same job, will change oxidation state during this transformation. Neutron diffraction, but also whatever diffraction, will not tell you any information about the oxidation state of cobalt, but X-ray absorption spectroscopy will. And so we have repeated the same experiment and the synchrotron in X-ray absorption spectroscopy. And in this case, again, this is a selected spectra collected in 2 days of experiment. The big difference here is it was a problem on an experimental point of view, because neutrons have a low penetration, have a high penetration depth in matter because they interact weakly with matter. So it was easy to construct an electrochemical cell to work with neutrons. It was much more difficult to construct an electrochemical cell to work in X-ray, particularly at the cobalt, and even worse at the iron K edges, because this material is absorbing very hard X-rays, and we needed to optimize on an experimental point of view a working cell which was very thin. We are speaking about 20 microns. Okay? The change of the Xanes tell that we are changing the oxidation state of the transition metal as expected. Very interesting is also the exact part. Let's look just to the Fourier transform here. We start from a bromine phase, which is a quite disordered phase, because what is clear is that the octahedral layers are well defined, but the tetrahedral layer can be displaced in different way, and different structural models are present. What do you see here? You see an impressive increase in the signal. And this is the first shell signal, and this is the less impressive increase. This is perfectly understandable because we are moving from a sample that in the first shell has tetrahedral and octahedral to a phase that we have only octahedral. So the number of oxygen neighbors in averages increases. This is perfectly understandable. But what is impressive is how the system becomes more structural and more ordered in the long-range region. You see that here we have noise. So in the starting phase we have signal up to more or less 4 Armstrong if we take into account the phase correction. While here we start having important signal even at much higher distance. This is because this system, the final system is very ordered and multiple scattering contributions are dominant in this case. We can make a very detailed analysis of the XANES and the EXA, seeing that we see again the 3 regions that we have seen in diffraction. And now we have to try to understand how it is possible, how does oxygen penetrate and migrate into the crystal. This is a nice picture, but this is a simple picture that shows you again octahedral, tetrahedral, octahedral, tetrahedral layers. In this case, we have put, you see that these tetrahedral are perfectly ordered. In this layer, all tetrahedral look this direction, okay? This is an oversimplified version. If this would be the case, this is not, but if this would be the case, you see that these ordered systems create a channel here. And during this channel, here there is room enough for oxygen to migrate, right? The point is that in reality the situation is not like this, because these tetrahedral are randomly oriented. This means that if, for instance, one of these tetrahedral will flip into this direction, it will close the door. And the oxygen conduction will be no more possible, right? Okay, and this is because you can see that we are changing between 3.5 and we tilting this tetrahedral will open or close the door of this solid. So our idea is that maybe there can be a phonon-assisted phenomenon. Imagine that there is a phonon in the solid that that makes this flip of the tetrahedral oxygen. Okay, it's just a guess. If we want to see this, we need to measure phonons, and the best technique to measure phonons is inelastic neutron scattering. So we run inelastic neutron scattering on 2 classes of material. The strontium iron that is able to conduct oxygen at room temperature, and the calcium iron that, although having exactly the same structure, is not able to conduct oxygen at room temperature. It must be heated at high temperature in order to work. And what we see, well, we see that at room temperature we have a soft mode at about 7.3 millielectron volt that is present in the sample in the sample that is conducting oxygen, and is not present in the sample that is not conducting. And if we are heating the sample, so if we repeat the same experiment at 620 or 1000 Kelvin, and note that here there is a phase transition, and at this temperature also the calcium iron becomes oxygen conducting, we see appearing this component also in the other systems. These are ab initio calculations that show the energy position of this soft mode. And what it is important is that these are, I have to say, ab initio calculation where we do not optimize the cell. We fix the lattice parameter B, which is a very important parameter. So we fix it, we don't optimize it, we fix it. Let's imagine that the lattice parameter is 14.6. And then make the ab initio calculation. And then we see that basically the fact that we have strontium or calcium does not affect the energy of these soft phonon modes. Okay? But we see that the determining fact is the lattice parameters, because at the given moment, so when the lattice parameters reaches values higher than 15.1 Armstrong, this mode becomes negative. What does it mean that it becomes negative? This means that this is no more a stable position. Okay? This means that when we reach this position here, the tetrahedral are allowed to switch from one position to the other. And if we look to the diffraction data, we see that the calcium iron at room temperature has this lattice parameter. So this mode is stable. This means that in calcium iron, the tetrahedral sides are not allowed to switch from one position to the other. So if the door is closed, it remains closed. While this is the position of the lattice parameter at room temperature of our oxygen conductance systems. And here it has not a true minimum, because it means that it can go up and down. And again, if we make diffraction on the calcium fair iron at 1000 Kelvin, we see that the thermal expansion makes the lattice parameters be increased, and here we have conduction again. Okay, so this is ab initio molecular dynamics, and we see the vibration of the tetrahedral oxygen in calcium iron. We see that we have thermal vibration, but all these vibrations are around the stable position. Conversely, in strontium iron, we see that we have migration from one position to the other. So I think these experiments combined with the theory has allowed us to understand what happens. Also, if we look the quasi-inelastic scattering, we see this is the Bragg peaks. This is the inelastic scattering, and this region is so-called the quasi-inelastic scattering. Here you see the phonons in the momentum versus energy plot. And while in the system which is conducting, you see the phonons that link the system to the elastic peaks, while in the non-conducting system, this mode is isolated. Okay, then we make the same experiment also on strontium iron. This is very nice picture of the single crystal of calcium iron. And now we change. We go to the subject number 2. We go to metal organic frameworks that in this case can be used for hydrogen storage, but also for other applications. So why MOF? Why MOF becomes so important in the last, let's say, 10 years, 10, 15 years? Well, because MOF are crystalline porous materials. So they are the same class of material as zeolites. The point is that this is a selection of zeolite type, and we say that the problem of zeolite is that they have an upper limit in the cage dimension, which is close to 15 Armstrong, at a more dramatic limit to 12 Armstrong to the pore size. This means that if we want to make catalysis, if we want to use this as molecular sieves, the molecule that can selectively be selected by these pores must be smaller than 12 Armstrong. If we want to work with bigger Armstrong molecules, we cannot do this job with zeolites. But we can do this with MOFs, and some examples of relevance in catalysis have been reviewed recently by Avelino Corma. And if we look here, this is the number of MOF structures that have been published in the last year. We see that starting from 96, 98, we have a dramatic increase. So I don't have the statistic of the last year, but I mean, it is quite impressive anyhow. So what is a metal organic framework? It is a combination between inorganic cornerstones and organic linkers. So this is the structure of the most famous one, which is MOF5. Basically, imagine that you have metal centers, like zinc in this case, and organic linker, okay? And you connect them together in a three-dimensional way. And in this way, you can build up 3-dimensional solids with crystalline structure and order. And what is amazing with MOF is the degree of freedom in the synthesis. So people that make synthesis can really enjoy about this, because remember zeolites. Zeolites, you know that there are a lot of zeolites. But all zeolites have the same units, which is a tetrahedral unit. And you cannot move from this. Conversely, on MOFs, you can have coordination 3, 4, 5, and so on. And it is just a selection. If you go to this review, in Chemical Society Review 2009, so some 5 years ago, you find under 31 different metal clusters, which is the inorganic cornerstones where you start building up your MOF. And what's about flexibility? So I took just 2 examples among these under 31. And here, the interesting thing is that we have a huge flexibility in putting the different metal inside the cluster. So with the same structure, this is a paddle wheel, this is a trigonal prism, and all these metal have been put in this condition. So we can imagine that we can make isostructural MOFs with different metals. Not all the periodic table for each unit, but still a huge amount of flexibility. Then we have flexibility in the ligand coordination. This is always the same in organic linker, and if we choose these cornerstones, or this cornerstone, we then up with MOF5, with MIL101, or with UEO66, which are completely different structure. More. Now, imagine that we can fix the inorganic cornerstones and change the linker, changing the geometry of the linker. So this is a linker with 3 coordination, this is a linker with 4 coordination, and with the 3 coordination we end up with H-1, while with the 4 coordination we end up with MOF 505. More. We can play with the linker length, changing the length of the linker. Same inorganic cornerstone, same geometry. We will change the internal volume. This is the series of MOF of the Yagi group, and this is the series of MOF of the Carpenter-Lillerud group in Oslo University, where we are strongly connected with. And then we can play with functionalization. So we can put here, this is the standard linker, we can put NH2, we can put NO2, we can put bromine, we can put, for instance, we're using this linker, this is the longer linker. If we substitute this carbon atom with 2 nitrogen, then we can link a platinum-2 square planar complex, or an iridium-2 square planar complex, or the copper-2 or the nickel-2, and this can make chemistry with this. And in this particular case, this is relevant because square planar platinum-2 is the most used catalyst in homogeneous reaction for this carbon-hydrogen cleavage reaction. And the idea is MOF like this could be able in the future to move the reaction from homogeneous to heterogeneous catalysis, which a huge impact in the industrial chemistry, because you have, at the end of the reaction, you don't have to separate the products from the catalyst, because they are in 2 different phases. Okay, so in this critical review of 2010, we have make a huge selection of examples where X-ray absorption and X-ray emission techniques have been important in characterization of MOF. Here I will focus only to one example, to one family of examples. But here you will have a quite broad overview, and people that are interested I can give them the PDF file. And this, the same is true. This is a chemical review on more general aspect of heterogeneous catalysis, but we have a full section on MOFs. Okay, now we focus on the H-cost of the UEO 66, 67, and 68 class of family. And here we will show how combining diffraction with spectroscopic techniques and with ab initio calculation, we can end up to understand how the structure is made and how it reacts to, for instance, solvent removal. Yes, I forget to tell you an important thing, that all these material are synthesized using a solvent. So when you synthesize, the synthesized material has always solvent molecule inside the cavities, and of course a fundamental step is to remove the solvent in order to use the empty space of the channels and the cavities. So these materials are stable. One very important experiment is thermogravimetry. So basically you put on a balance your MOF, and you flux in oxygen and you eat. And what you see is a weight loss. So this first weight loss is the fact that eating the solvent goes out. And this is very important. This is the stability plateau. This is the plateau where the MOF is stable. And these two MOFs are stable up to 550 more or less degrees. And this means that you can use them for whatever application not exceeding this temperature, because here is this huge drop is related to the fact that you are breaking these bonds here and you are burning the organic molecules, and you end up with CO2, water, nitrogen, and so on, and you have destroyed. And here you have zirconium oxide as remaining stuff. Okay, so we can follow the solvent removal reaction with exas. So this is the inorganic cornerstones. Of course, if we make exas, we have a local picture around only the metal atoms, while with diffraction we have information on the whole structure. And what we see is that this is the first shell, zirconium, oxygen distances. And this is the second shell, zirconium, zirconium. And this is the third shell, zirconium, zirconium, on the diagonal of this. This is a perfect octahedron. So imagine to have an octahedron with 4 zirconium in square planar plus 2 zirconium like this, connected with oxygen as depicted in this picture here. So the interesting thing is that we have a huge change in the zirconium distances upon removing the solvent. And these changes were not observed by X-ray powder diffraction, because these are the thermal temperature resolved X-ray powder diffraction experiment, where we see always the same peaks. Only at the end the system changes, but here we are destroying the MOF. So we have to understand why exas see a very huge contraction of this. So we have a very huge change in the local geometry that is not observed by X-ray powder diffraction. Again, this is diffractograms of the synthesized blue and desolvated. You see exactly the same peaks. You just see that this peak here is a low intensity. That's typical of porous materials, where you are removing the disordered electron density inside the pores. The basal peaks goes down in intensity. This is known in zeolites as well. And then here, this is the exa. So you see a small difference here, but a huge difference here and there. So how is it possible that exas is able to see something that X-ray diffraction is not? Well, this has been, in order to understand this, we needed something like 19 pages of chemistry of material, where we combined X-ray powder diffraction, exas, and ab initio calculations. And basically, our model is the following. Well, yes, sorry, I forget to tell you an important thing. This is infrared. This is infrared spectroscopy. And infrared spectroscopy tells you that in the synthesized material you have OH groups. And these OH groups are disappearing when you remove the solvent. And this is very defined OH groups, because this peak is very sharp and is not broad. So there are isolated OH groups, and these are these OH groups here, basically. So what happens is that we have, imagine an octahedron. So an octahedron has 8 triangular faces, right? 4 in the bottom and 4 in the upper part. In 4 of these 8 phases, in all of these phases you have a Mu3 oxygen that is bridged with 3 zirconium, and in half of these phases you have an OH groups. And when you make the desolvation, you remove the solvent, but you also remove 2 framework water molecules. So this goes out as 2 water molecules, but before there were framework oxygens that goes out. This implies a distortion of the local geometry of the octahedron, where the local coordination in first shells moves from 8 to 7. And it implies that you move from a perfect octahedron where all the sides, where you have 12 equivalent zirconium distances and 3 equivalent diagonals, into a system like this when you are squeezing along one diagonal your octahedron, and so you end up with 8 short zirconium distance and 4 long one, and you have 2 long and 1 short diagonal. Okay, this is the idea of what I show you, but of course this should be, we are speaking of, this contraction is a 0.2 Armstrong, which is amazing. So this must have been seen by X-ray diffraction. Why we cannot see this by X-ray diffraction? In X-ray diffraction this would lead to a reduction of the symmetry, so you should see the appearance of new low symmetry peaks. But we don't see anything. Why? So there are no peaks there. Why? Well, because this contraction will be random. What does it mean, random? Each octahedron has 3 diagonal. If all octahedra would have been squeezed along the same diagonal, then this would have been an ordered squeezing, and this would have been seen by X-ray diffraction that looks the long-range order only. But if this is random, this has no long-range order, and X-ray diffraction just see an increase of the thermal ellipsoids, but is not able to see what a local structure like EXAFS is able to see. Okay, I will not show you, discuss these results because they are very boring, but it is the comparison between EXAFS and powder diffraction, between powder diffraction and ab initio calculation, and between ab initio calculation and EXAFS, in order to check that the 2 experimental, the theoretical ground agrees with them. And it is very important because EXAFS, I have no time to enter into detail, but EXAFS and diffraction see 2 different things. Okay, then in order to locate this hydrogen atom that we have seen by infrared, and it is fundamental in our model, we need to run neutron powder diffraction and see how it is important to see that powder diffraction is able to give high signal, even high IQ exchanged vector. These are the data that we collected just recently at ILL that are under analysis. Okay, then let's move to one application of this material, which is hydrogen storage. And here we will discuss, so these are the 2 homolog structures where we have the same inorganic cornerstones, and simply we double the length of the linker, changing the linker molecule. Okay, so of course we will include this material as tetrahedral and octahedral cavities, and in both cases the change of ligand will benefit an increase of internal volume from 7.5 to 12 Armstrong and from 12 to 16 Armstrong. So you will have more internal volume available that can be used for molecule storage, in this case for hydrogen storage. We check the structure, so the structure is exactly the same, simply that you will see the peak shifted because the lattice parameter has been increased in this case, so all the peaks are squeezed low to theta values. We have the same thermal stability, but we will have a big difference in the porosity. So this is BAT experiment, so isotherm of nitrogen absorption. We can see that in the UIO 67 with the longer linkers we have a much higher internal volume. We repeat the EXAFS experiment, and exactly the same feature has been observed for this material. Here is the quantitative measurement of hydrogen absorption, where we go up with this material to more than 4.5% in mass, which is not the record, but it is close to the record. In order to study the absorption location of this hydrogen molecule, we run in elastic neutron diffraction. This is elastic neutron diffraction at ELL on EN4 instrument. And then we are not happy about this. Remember the flexibility. I'll show you the relevance of the flexibility in changing the ligand length. Now we use the flexibility of changing the inorganic cornerstones. We were working with zirconium till now, but the chemistry tells us that in principle we can do the same job with hafnium. And why is hafnium interesting? Well, it is interesting because of use as potential interim radioactive waste scavenging. You know that in the Western Europe, several countries are dismissing a lot of nuclear plants, and so we will have to deal in the future on how to store these radioactive systems. And one of the ideas in the past was to use zeolites because of the porous nature. We can absorb a lot of radioactive molecules like iodine and these kind of things. We can do the same with MOFs, of course. But our idea, zeolites are limited by elements, so we have only low Z element, oxygen, aluminum, and silicon. Thank you. So this means that they are low X-ray and gamma absorbers, and they are not able to absorb neutrons. But the same holds for UO66. But if we changed from hafnium, you can see that hafnium has a very strong absorption cross-section for neutrons. This means that if we are able to synthesize the hafnium homologue of this MOF, we can have a porous scavenging materials where we can put inside our radioactive molecules, and that can be used itself as shield, as partial shield for emission of gammas and better emission of gammas and neutrons. Material has been synthesized. It has exactly the same pattern. These are much better pattern. This was laboratory. This is synchrotron. So this is ESRF Swiss Norwegian beamline. That's the beamline that is led by Professor Dmitriev, who just received last week the laurea honoris causa by this university. He's a former professor of this university, and now again honoris causa professor, and we will collaborate with him for sure. So this is high quality powder diffraction collected there. We see here the absorption isotope, and so the system is stable also with zirconium at the same temperature. We have basically the same good internal volume, and we have a good thermal stability measured by temperature resolved diffraction. And again, the exas, so you are familiar with this too, we discussed it before, and with the hafnium is exactly the same story. This is more detailed on the exas data analysis, but this is not finished because we can, our fantasy is not limited, and if we could be able to make a linker having boron inside the linker, then this ability to stop neutron will be even more important. This has been done, so we change it from this standard ligand into this ligand that has boron atoms in the green one. This is the X-ray pattern. It's not perfect, but it is there, and this will be really impressive for stopping neutrons. So this is the end of my talk. I just want to tell you that we just started from my official presence in Southern Federal University in Russia. Started in January the 1st, and in these 2.5 months. So we already have 2 papers with my name with the South Federal University. One appears in JPhys MC, one appears in Nanoletter just a few days ago. And of course, we plan to have much more in collaboration, of course, with Alexander Vladimirovic's group, but I mean with all people that are willing to collaborate to this adventure. Thank you. Many thanks for your kind attention.